if you want to. Yeah. Okay. So you can, Jacob will keep doing the push of the update. We can work on our laptops. Yeah.
Where was the reset back to factory?
That's under the File menu, Load Factory Defaults, under the File menu. But that'll disable Cell Blender and Gamer.
I know.
Yeah.
I did something wrong.
Oh, okay. 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 So you can fire up your Blender. And for some reason, I'm not getting the splash screen anymore, but that's all right.
The screen doesn't come as easily on Mac.
Yeah, it usually does, and I don't know why I'm not getting it now. I usually get the splash screen. I didn't get it. No splash screen. But it doesn't matter. Okay. I don't think so. I don't know. Okay, if you fire up Blender, we're going to begin our next example. And we're going to be building a cell that has two organelles inside of it. And then we're going to be doing some fun biochemistry with transporters and translocators and enzymes and things like that. Kind of make-believe molecules, but probably reminiscent of many of our friends. Okay. So first, your screen probably looks just like this with these objects in it. So I'm going to use the A key to toggle on and off and eventually get everything selected. And I'm going to hit X to delete all those because we don't need them, and they're gone. And so then under the Cell Blender tab, when you click on it, if yours is like mine, it says Initialize Cell Blender. And you click on that, and then you get the Cell Blender panel. And like everything, we begin with molecules. Sometimes we begin with geometry, sometimes molecules. But you can't have reactions until you have molecules, and you can't have anything fun happen until there's molecules. Carl Sagan says we're all just a pile of molecules. Okay. What's that?
Star stuff.
Star stuff. And then we're a collection of molecules. I'm a collection of molecules named Tom Bartol.
Well organized.
Yeah. Sometimes. Okay. So under molecules, we're going to add a molecule. Our first molecule is going to be called L for ligand. And this molecule is a Molly molecule, and it's going to have a diffusion constant of 2e minus 6. And
Bring down the light a little bit?
yeah, and I need my cheat sheet. I'm good for a little
Isn't that it there?
while. No, the notebook in,
Oh,
your,
okay.
in your notepad.
Okay. Should turn it on.
Maybe that's as low as it goes.
Oh, that's
ah,
low.
there it is. Okay.
Okay.
Okay. Is that enough light for everybody in the back at your desk? You're happy? Okay. Okay. Yeah, there it is. Yes, that's it. Okay, thanks. Okay. And then we need to release these to have any happening. So under our molecule placement panel, we're going to add a release site, and we're going to release molecules of L. And let's release 1,000. We're going to start with a point source, again like last time. So through repetition, we're going to get more familiar with these. So some of this is going to feel a little repetitive at first, but then we're going to quickly diverge off into unexplored territory. So then at this point, we could go to run simulation, and to start with, we're going to run for 1,000 time steps with 1 E-6 for our time steps, so the defaults are fine. But it won't let us run until we save. So I'm going to hit Control S to save. And I'm going to call this the CMW Demo 2 for Cell Modeling Workshop Demo 2. And then save it. So mine remembered the directory I was saving in before because I'm still on my Mac. You guys are now on a new setup. You might want to navigate and make a folder where you put stuff. Okay, and now we're ready to run. So I'm going to say export and run. And there it goes. And then I can say load visualization and hit play. And there's our 1,000 particles. So now let's make a cell to contain these diffusing molecules. So go to the Model Objects panel and click on the center of the cursor control to make sure your cursor is centered. And then the second kind of object over is the Ecosphere, construct an Ecosphere. Click on that. We'll get a mesh that looks like this. And at the bottom of your tool shelf will be some controls for the Ecosphere. And the top one is called subdivisions. Set the subdivisions to 3. And you can see, or 4. I'm going to choose 4, I think. Yeah, 4. And the more subdivisions you do, the more triangles you get in your Ecosphere.
Yeah, we can make sure it's
but 4 is a good number. And then the size sets the radius of the Ecosphere. Set your radius to 0.5. Okay, so we have our Ecosphere. Now we're going to change its name to cell. So in the Model Objects panel, before we don't add it as a model object yet, we're going to change its name to cell, lowercase c-e-l-l. And after you type that in, hit enter. And then now we're ready to add this as a model object. So hit the plus button next to the model objects list. And now you'll see the cell listed. Okay. And now you'd be ready to run it. And now when I load the visualization, now all the particles are inside, but we can't see them. Okay,
Why can't we see?
you've restarted, now it works?
It's bad.
Cool, all right. I've seen that happen. I was going to suggest that, yeah, next. Okay. Really?
Just restart it, it's okay.
Yeah.
Okay, so apparently everyone
Yeah.
crashes on the first one?
I don't know, yeah. So nothing yet, so 0 yet. It's a point source to start with. Okay, so make sure you save a lot because we might have crashes.
Well, obviously you do, because mine's not bounding. I see these outside the,
No, but I think that's just on the edge.
no, they're way out.
So to be able to see the particles inside the cell, we're going to go back to the Model Objects panel
You probably have to,
and make sure the cell is selected. So click on it in the list here to make sure it's selected. And then below the Model Objects list is this object options. Open that up. And we're going to show it as a wireframe.
Seems like yours isn't bounded and mine is.
I feel like this is okay. So, oh, you got wireframe?
Yeah, so choose, so there's two different ways to display wireframe. One is to put, one is to just show the maximum draw type, or the first drop-down menu has an option of bounds, wire, solid, or textured. Choose wire in there.
How do we rename it to equal cell?
Oh, if you've already,
Oh, I'm here, okay.
if you've already added it as a model object, you'll need to probably,
Oh, okay.
yeah,
If you
rename
select cell
it.
and then add again, then it comes up.
Right,
Same thing.
right,
So object options, and then wire. Oh, perfect.
yeah.
But is wire, what about bounds?
Why is it bound? We haven't set it to be bound yet.
If you said bounds, then you get a big cube, which is the bounds, the bounding box.
No, as in the morning example, we had to go to the molecule and then set it to be bound by the object for it to be bound. But now it's just being bound naturally.
No, it's not.
Bound?
Oh, really? Mine is bound. Oh, sorry, I meant back in the molecule placement.
Because it's the bounding box.
The longest X, Y, and Z dimension in that object, something like that.
It's the bounding box of, it's a circumscribing box, basically, right? Yeah. Okay.
So when you add an object, does it automatically make those, the boundary of that object, something that molecules will reflect on?
Yes.
That's the default?
Yeah. So one thing that's demonstrated by what we just did, as Bob is pointing out, is that we have a point source of release, and we put a sphere around it, and we didn't say that the particles were released inside the sphere, right, in the release site. We just said we wanted a point source at 0, 0, 0, and we made a sphere centered on 0, 0, 0. And the default properties for any surface or object in here is to make it be reflective to diffusion.
Oh, so how do we do that?
Yeah, it's the default setting.
But mine's not reflecting diffusion. Mine's actually letting it diffuse out. And yours is too, or at some point it was.
No, that was before I added the sphere, but I hadn't run it yet.
Can you show where you get?
You have to run it.
Run simulation with the sphere.
Yeah,
Can you show where you can set the reflective property up there?
yeah,
Thanks.
yeah.
And how do we make this, oh, it's in the selection method, sorry. Yeah.
Well, maybe it happened now.
So that might be a,
Where's
The
the?
reload visualization, yeah, now it's
mine
contained
is
inside.
reflective.
yeah,
Mine is always reflective, but I want to see where the setting is to not do that.
okay. So under surface classes, you can add a new surface class and name it reflect,
Now you want to name this one?
or I'll call it trans P, right?
Yeah.
And then click on a property And the default new property, if you make a new property, is transparent, since the default regular property is reflective, right? So we've made a new property called transp that you can, and then you could apply that to the sphere. So that's under that the control panel right next to this is called assign surface classes. If I assign the transp to cell, right? Yeah, but I'm not going to do that here, so I'm going to get rid of that and get rid of that. Yeah. And there's also an absorptive surface class, and you can make a surface reflected to one thing and absorptive to another and transparent to another.
Is there a way to make our wireframe less obtrusive to the?
Well, let's just we're going to do that. We're going to do that later.
All right.
Okay.
If you press A, turn off selecting everything, then it's not orange. Then it moves a bit back.
Okay. Okay. So now we have a reflective sphere around our diffusing particles, and now we've made it into a wireframe so we can see inside, and we can see the particles diffusing inside until they reach the boundaries of the sphere, and eventually they'll become uniformly mixed. Okay. Okay. So these are our ligand molecules L. Okay. So now let's add the one of the two intracellular organelles. So now with a spherical cell.
Intracellular ligand.
Yeah, exactly.
Well, why can't it be an intracellular ligand? We're playing the game here.
Ligand is fine.
Yeah, it's fine. It's just kind of
Yeah. It's just whatever. So now back into the model objects panel. Center your cursor, again with the center cursor button. Add another icosphere. And now it'll be just like the first one. It'll even remember the subdivisions you gave it. But let's give it a different radius. This one is going to have a radius of 0.1. Okay. And there it is. And you'll see when it's created, it has these 3 arrows on it, red, green, and blue arrows. That you can click on the head of the arrow and drag the organelle a little bit off center, and kind of move around and make sure that's really inside and hasn't been moved outside. Okay, and then name this one Organelle 1. Organelle 1. And add it as a model object.
What size did you make that?
And I gave it a radius of 0.1.
Did you rename it first?
Yes.
So rename.
Yeah. So the Organelle 1. So it's important when you create new objects that you rename them before you add them as a model object.
You can always rename it up top though, too.
Yeah, you can rename it up top, but I think, doesn't it get confused?
It takes it away and you have to press adding it.
Yeah. Right.
If you used it, referenced it anywhere else, and then change its name, that name won't follow.
Okay.
Yeah.
It won't follow.
Yeah.
All right. That makes sense.
Yeah. Okay.
Do you need to press adding it? No?
Interesting. We just kind of stopped.
And then for the for the object options for this one, I'm going to say add a material. I'm going to leave it visualized as solid, but I'm going to click on add material.
Oh, we have it now.
Oh, if you add an object, it reinitializes all your objects and takes in your renaming.
Can I just delete all that?
Yeah, I guess.
Yeah.
What do you change the?
Right click.
Yeah, you can hit the minus sign to delete it.
Oh.
And I'm going to make this one, make it be a transparent material, and then set the object to be transparent. So we have a transparent material that's applied to the object that is also transparent, and then I can set the degree of transparency. I'm going to set it to 0.2. And now our organelle is a little transparent guy inside. And we could have done this to the outer cell, but for now I've purposely left it as a wireframe. Okay?
Where's transparent?
You add a material.
Oh,
Say add material, and then you can make it be transparent. Okay.
You guys need help making your transparency?
Yeah.
Yeah, click on add material.
What's the difference between object transparent and material transparent?
So there's kind of two different visualization modes in Blender. One is like a photorealistic mode, and one is I guess this is kind of this is like the object editing visualization, right? So you don't really want the objects to look totally realistic, like they're going to look in your final photorealistic rendering. You're just designing your object, and you want to be able to visualize the wireframe of it and all kinds of stuff. So for that mode, you might not want to have the transparency be visualized. So they have a separate option for that. And so, but in order to make the object transparent, it has to have in the modeling view that we have here, we need to have both things be transparent. So the material that it's made of has to be a transparent material,
Yeah.
and we have to say in the modeling view, make it transparent.
Yeah.
It's kind of funny, but that's the way they do it in Blender.
Yeah.
Yeah. Okay. Okay. So now in the molecule placement, under our release site for L, Bob pointed out that all we had to do is put the sphere around it, and the diffusing particles could see that reflective sphere and bounce off of it. But now we're going to tell it, now we don't want to do that. We're going to release inside the cell. So change the release shape to be an object region release shape, and make it be the cell with a release probability 1, constant number 1,000. And so now this is going to release the L molecules uniformly distributed within the cell. Okay, and we have our organelle in there. And now let's go to the plot. So if you've done that, now I'm going to go to the plot output settings, and I'm going to ask to count the number of L molecules in the world.
And also of each of the objects.
Okay, and I'm also going to ask to count how many L objects, L's there are inside an object now. So instead of counting L molecules in world, I'm also going to count L molecules in an object, and the object is going to be organelle 1.
How did you get that menu?
This is under the plot output settings.
Right,
And then I click add 1.
Oh, I see.
And then molecule L in world for this one, and molecule L in object organelle 1 for the second one, okay?
And now I got 8 of them inside the organelle 1.
Right.
So you're gonna leave for now organelle 1 completely porous.
Inactive.
Well, it's not porous, so I'm going to explain something. So let me run mine, because you're observing something important, which is the point of teaching it to you this way. So now when I do my plot output settings, and so on my Mac I do have XM Grace. You guys might not. My matplotlib plotter works though, and does
Yeah, so does mine.
and so does yours. Okay, so I'm going to use my matplotlib plotter. I'm going to say plot, and this is what I say. So there's 1,000 in the world because we asked for 1,000, but 12 of them are inside organelle 1. But we told the tool that we wanted to release inside the cell. Okay. Well, organelle 1 is inside the cell.
Yeah.
So it released inside of the cell, which includes the interior of organelle 1.
Yeah.
Okay? But that's not what we want in this case. We want to do something different. We would like to release inside the cytoplasm of the cell, but not. But that excludes the interior of organelle 1. So there's a way to do that.
Yeah, I see. That's why I'm thinking.
If we go back to our release site, molecule placement for release site 1, instead of releasing inside just the cell, we're going to say CELL and then square bracket, capital ALL, cell all, minus organelle 1 all.
Yeah, that makes sense. Why do we need the O?
That just makes it more specific about how the Boolean operation is performed. And there's some other options
So
for.
if we, the default is not O then?
Well, the default is all, but when you do Boolean, you have to explicitly say all.
How do I go back to the size of the organelle?
So you.
Is that a shape maybe? Or are you already there? Sorry.
So if you've accidentally made your organelle 1 the wrong size, to change it after the fact, you can use the numerics panel and change the dimensions, right? But now the dimensions, the XYZ dimensions, are now the diameter values and not the radius values.
Yeah.
Okay. Okay. Okay, so now I've said cell. So for the where to release, which is called object/region in the molecule placement panel, I've set it to cell all minus organelle 1 all, and so that does a Boolean difference operation where it subtracts out the shape of organelle 1 from the whole shape of the cell for where to release. Okay, and if we run now and say export and run and reload and then reload the visualization. Now when I zoom in and look at my organelle, it's pretty apparent that there's none inside there, but to be sure we can do our plot.
Oh, this is stopping from even diffusing inside.
Yeah.
Actually, I can't get any diffusion.
Why is that obvious? I mean, we made it transparent just because we didn't initialize it.
Oh, transparent is just the visualization transparent,
Well,
not to
we said
make it
both.
reflective.
I thought we said them both transparent. We said both the object transparent and the material transparent.
Oh,
Yeah, but that's visually
that's only the visualization. not the diffusion property.
Diffusion object and material for visualization.
I'll explain.
Okay.
Yeah. I could, yeah, these are confusing terms because transparency means in different contexts.
Transparency refers to light, no?
Yeah, but it could also, but we can make it be transparent to diffusion also, so that the particles, but we have to specify that. But he thought that that's where we specify it. He didn't hear me explain to you about the.
Particles coming into my organelle.
Right, that's correct. So now after you've released this way using the Boolean operation, when you look at your plot, you should see 1,000 molecules inside in the world and 0 inside organelle 1.
And so my matplotlib that still doesn't work, but that's fine, right?
Yeah, I don't know why it doesn't work. Maybe get Jacob to So save early, save often. Save early, save often. Yeah, I'm not sure what.
I just want to make it aware that
Yeah.
people are getting frustrated.
Yeah.
So we definitely run the simulation.
That's like throwing some real biology into it.
Okay. So next step.
Oh, you didn't set up?
Oh, you know why?
No.
Like I found him. He's actually outside.
Why did you do that?
Why did you do that? Well, because when I shrunk my
Oh, so it's just ended up outside.
Unfortunately.
Okay.
And then what do you
So now let's.
And now,
We're going to make another molecule called R. So under the molecule panel, hit the plus button to add a new molecule. This molecule is going to be called R. But it's not going to be a volume molecule. This is going to be a surface molecule. Okay? It's a surface molecule, and it's going to have a diffusion constant of 1e minus 8, which is a realistic diffusion constant for small molecules in a membrane. It's on order of 1e minus 9, 1e minus 8 kind of speed.
Are molecules usually slower inside the plasma than in the membrane?
So it's lower diffusion if they're in the membrane.
It's slower in the membrane because the membrane is higher viscosity.
Yeah, as in, so, okay, yeah.
But it's also 2D diffusion, not 3D diffusion. So it's measured differently.
That's what I'm saying.
It's measured differently, and the equation for 2D diffusion, the analytic solution for 2D diffusion is a different function
Oh, yeah.
than it is.
It's closer, actually.
The units on diffusion constant are the same, but the equation that it plugs into is a different equation. So it can be confusing to relate the two.
Yeah, can you relate the two?
There is a way to relate them, but
It's not.
yeah.
Is it because I
Okay, so
So many weird things happen. It's very strange setup for time. Working, they're not working.
yeah, the bundle seems to be crashing sometimes, and
I know,
sometimes the
I-
plotter works, sometimes not. I wonder what's, yeah.
I'm wondering if it had
Yeah.
something to do that people had it up and running while it was getting copied into place.
Oh,
What's that? I mean,
I thought
had it
people
up and
quit.
running,
I
but
thought
they
people,
didn't.
but I told people to quit, but maybe they
But
I
didn't
went
quit.
around and took everyone down. Oh, they may have started up again because we didn't get.
Yeah,
the
there was
sign.
there was all those errors coming out, so I think people probably still had it open while it was copying it into place.
So they're not fully copied then.
I'm not sure.
Yeah.
I've heard a
Okay.
suggestion from somebody that maybe it'd be a good
Okay.
time for a break.
Well, that's what I was.
Okay.
And then, yeah.
Okay. So it seems like some people are having a little bit of trouble with it crashing. Yeah, so let's have a little bio break and recoup time, and we can get our hair pulling time over with.
Save
And
what you have.
yeah,
Save it in the file, because we may end up putting the limit.
yeah. So save. I think they should quit. So save, and then hit Control Q to quit and say quit from Blender. And we're going to make sure everyone quits.
Do we need to quit on a laptop too? I guess?
Yeah, you don't need, if you're on your laptop, you don't need to quit, obviously, right? But on the workstations, please save your work and quit.
There's some cookies, so help yourself.
So I mean, Xing out of it.
Okay, we continue where we left off. Hopefully, we can keep moving along here. All right. So just to remind ourselves, what we just did was add R and
So they need to open their files again.
yeah, yeah, fire up Blender. And when the splash screen for Blender starts up, it might show the recent files in there. And pick the one you want. I called mine CMW Demo 2.
Maybe you have a good OS.
Okay. So where we had left it was we had added the organelle and made it so that the L molecules are released inside of the cell, but not inside of organelle 1. And we made a plot that demonstrated that we didn't have molecules inside organelle 1. So this kind of piecewise, stepwise, disciplined approach to building a model piece by piece and verifying that each piece is as you expect it is really important. Process engineering or complex systems engineering, because that's what we're doing here. Even the simplest model is made of many moving parts that can quickly get out of control and start going wrong, and then you have a hypothesis about what's going wrong, but your hypothesis is wrong, and so what's really going wrong? So oftentimes it's good to break down and start from the beginning. Maybe start over again, start from scratch. But so we've learned this over and over again, so we build piece by piece and verify each piece before we assemble pieces into bigger parts of the whole. Okay. So then next thing we need to do is add a molecule. Maybe you've already done it, but it was a molecule of R. It's a surface molecule, and its diffusion constant is 1e minus 8. And this is the first time that we are going to be working with a surface molecule. And you'll notice that in the molecule list, there's a little icon that pops up next to it that looks like a little grid. That's supposed to signify that these are particles that are going to be on a surface, as opposed to the volume molecule L. Its little icon looks like a little bouncing ball, kind of indicating that it's a particle that could diffuse and bounce off of things. Okay. So now under our molecule placement, we're going to add a new release site. I'm not sure why. It's called release site 1 again. We have a little bug. Bob and I noticed it yesterday, and then we tried to replicate it, and no matter what we did, we could not replicate the bug. But now in the
Now
class.
it's
I've seen it a couple times.
And it's
I
on my
said
laptop as
release
well.
site two, perfectly happy.
Yeah,
That's what was happening on.
we're not, yeah,
Linux
any,
seems
yeah.
easier for me.
I don't know. We'll figure it out, but so just change it to release site 2. And this is going to be, we're going to release R.
Okay.
And now, when we release R, when we say R, now the panel, the options change because it knows it's a surface molecule. And there's an option for the initial orientation. And there's 2 possible orientations. One is top front, and the other one is top back. What does that mean? So I'm going to go over here and show you what that means. So here's a side view of a membrane. Here's a molecule that I'm going to put in the surface of the membrane. Molecules in the membrane act like transmembranous proteins. And they have 2 domains that we imagine. One's called top, and the other one's called bottom. And then the surface itself has a front and a back. And so when I put my molecule in the membrane, I can either have it oriented this way or oriented that way. Why would we go to the trouble of doing this?
So it can interact one way and not the other way?
Yep. That's for sure. That's one reason. And another reason is that there are actually membrane proteins called flipases that go around looking for misoriented proteins and flipping them, or going around looking for any protein and flipping it anyway. And we wanted to be able to simulate lots of different things. And so we built in this capability to be able to specify the orientation. And we're going to make use of this orientation further in this demo,
But you can only have.
so that we can make transporters and translocators and things like that. So, okay. So the front and back of the surface is determined by the surface normal vector, right? Which comes from the right-hand rule. So another good reason to make sure your objects are created with surface orientations that you know what they are. Doesn't really matter that they're all outward facing or all inward facing, as long as you know what the normal vector is. But just to be consistent and happy, it's really a good idea to always make sure you have a surface with outward facing normals. Okay.
So front is always the normal direction.
So the front side is always the side from which that it's against from which the normal vector arises, right?
And how does that relate to the inside or outside?
So if your object is created with outward facing normals, then this is the inside and this is the outside in standard physics and computer graphics convention. Okay.
So you're limited.
And so then your front would be your outside.
So you would normally want to make your surfaces with outward facing normals, so that the front is outside. So this would then be the front of the surface, and this would be the back
So that means top
of the surface. So this would be top front. And I personally have, since the top and bottom, the top and back of what's top and what's back, or top and what's bottom of the molecule is arbitrary. It doesn't really matter what you do, but I have a convention where I always place my molecules in the surface with top front orientation, so that it's really clear as I write my reactions and I make my transport happen, where particles are being translocated from one side of the membrane to the other, since when I write my reactions, I write them as if I'm imagining that the top is facing outward of whatever organelle I'm imagining that thing's going to go in.
So for
Right.
reactions, we can have top front plus top front of this molecule plus back of this molecule, or something like that.
Yeah.
Okay. So what I
Yeah,
noticed-
and you're gonna see that when we write our reactions.
What I noticed is you can only have two domains this way. I mean, if you have something like ATP synthase or something where you want, like top, middle, back, or like, you have two things within back, how would you?
So you can have any number of things interacting with either side.
Or you want like back to have two different functions, right, or something?
You can have any number of functions on any sides just by how you write your reactions. So this doesn't limit you in how you do that, right?
And then if you had a vesicle, the inside of that vesicle is topologically equivalent to the outside of the cell.
That's right. So that's why this doesn't say out and in, and this doesn't say luminal side, cytoplasmic side. This says top, bottom, front, back. And it's always like this for any object. And it doesn't say that this is luminal. This doesn't say cytoplasmic. It's just front, back. We purposely made the terms generic in this way and unambiguous.
Yeah.
I think this is unambiguous. Whereas if I said luminal or cytoplasmic, right, that could be ambiguous. And especially in mitochondria, where you have the outer membrane, the matrix, and the inner membrane, and the space between the outer membrane and the inner membrane, right? And then outside that, the cytoplasm of the cell, and outside that, the extracellular space, right? All these different compartmental spaces. So, one reason that we've made this demo is to show you, give you, we all know that cells go to great lengths to separate self from non-self, or self from other, or self from other parts of self in tissues, right? And signaling between them. And it's all about compartmentalization and sequestering and secretion and transport. All these things happen in cells. It's part of the way they organize themselves and try to defeat entropy, right? This is the battle against entropy right here. Okay. So, but we only need to worry about these orientations in the context of surface molecules and how they interact with each other and with other volume molecules. So volume molecules don't have this ambiguity because they can only encounter each other if they're in the same volume. And then the orientation doesn't matter. They either bind, they encounter each other, and they either bind or they don't, right? So that's why with the reactions that we've made so far and the topologies we've made so far that consist of only volume molecules, we didn't have to have this discussion. Okay. Okay, so top, front, and since they're surface molecules, it has to be on some object, right? Don't have any other option. So we're going to say for the object for R, we're going to say organelle 1. And we're going to release 200 of those.
200.
200. Okay. There's also an option of releasing, instead of by constant number, by concentration or density. So the term concentration would apply if it were a volume molecule, because that would be number per volume. It's usually how you think about concentration. Some people think about that as a density also.
Yeah.
But the term density, it usually applies to, or you think about it in terms of number per square micron, the density on a surface. But maybe not. But I think it would be unusual to think about that as a concentration, though. a surface density in terms of concentration. I don't know, you know, maybe these terms are used in different contexts by different people to mean different things. But, you know, we're among friends here. So, and so in MCell, if we were to do this by concentration or density, it would be, the units on it are number per square micron. Because the length unit in MCell is microns. So square microns would be an area. Okay. But when we talk about concentration, though, in a volume, that's moles per liter.
Yeah.
Right? Not number per cubic micron. Just to be clear. Oh, one thing I should point out is that next, you may have noticed next to each of these buttons, there's a little eye. And if you click on the eye for a given control option, some help will pop up that explains some of what I've been saying. Okay, so I'll just put that away. Okay, so 200 at a constant number. Oh, another thing I should say is that when you release by concentration or density, what you get is a probabilistically generated concentration or density. And rather than you won't get an exact number every time for every seed. It'll have a mean value of what you've specified, but it will vary greater or less according to the binomial distribution of what number that would be equal to. And you would get plus or minus square root of that number, kind of what you would expect from a binomial distribution. Just to know. So if you know you want to have an exact number, you can calculate your own surface area, your own density, and figure out what number that would be exactly, and not vary but from one simulation to the next by seed, and you could then put in that number. So that's what we're doing here. We're saying I want 200. Okay. And so now let's go to the plot output settings, and we're going to count and we can count them in the world. We're only going to put them on Organelle 1, so you could either count them in the world or on Organelle 1. I'm just going to say world, whatever you like. And now I'm going to say run the simulation, export and run. There it goes, reload. And now if we look at Organelle 1, it has some nice green particles on the surface. And if I run the simulation, you can see them wiggling around on there with their slow diffusion constant. Okay? Next. Next step is our receptor R is involved in reuptake or sequestering of, binding and internalization, right, of L. So we're going to make a reaction for that. And this is our first time making a surface reaction, or a reaction between a volume molecule and a surface molecule. And so add a reaction, hit plus, and we're going to use some special syntax that we've invented for expressing this concept of front and back, of how the interaction can occur in a spatially specific context. And the BioNetGen language has a different way of expressing this, and we're trying. We invented our syntax at about the same time, unbeknownst to us, that Jim and his colleagues were inventing the BioNetGen language. And we have a slightly, it's a compatible but slightly different way of expressing it. And in our work, our ongoing work right now and into the short-term future is to reconcile this and merge the two concepts together in a seamless way, but we're not quite there yet. But if there's time, tomorrow afternoon we might show our initial progress toward that in the tool. Okay, so, but how do we do it with MCell? So when you write your reaction, I'm going to say R, and then to express that R is with its top outward, I use an apostrophe. So I say R, and usually I say apostrophe, or sometimes I say tick when I'm talking about it. So you say R apostrophe plus L apostrophe. So that means L will be, that means the top of R is accessible to L approaching from the front side of the surface. And that would be true if the molecule, if L were oriented in the surface with its top front, right? But we haven't yet put R. Oh no, right. And when we placed R, we already said R was going to be placed top front, right? So since R is placed top front, then this reaction means L also approaching from the top side of the membrane. So this is basically L binding to the top side of R, okay?
Yeah.
And this is going.
Wait, what is it? L prime?
So it's like L prime, but the prime isn't really a prime in like you would use it in mathematics expression. This really means the top front orientation.
But
So
L is a
if you want
volume.
Approaching from the
But I thought it's just a molecule, right?
Yeah, but it's a spatially. We're doing a spatial reaction diffusion simulation in a spatial context, and standard chemical notation, kinetic notation doesn't include a spatial context in the notation. So we've added metadata. Or we've enhanced the expression of a.
I guess what I mean is
Oh.
R prime plus L should lead to the same results,
Right.
right?
Yeah, no matter any L is going to be L.
No,
No,
since L is interacting, this isn't saying that L is top front. It's saying that L is, since we know R is a surface molecule, this is saying that L, which we know is a volume molecule, is on the same side of the membrane as the top of R.
But if L was on the other.
When we don't want it to react.
Exactly. So it's unnecessary. As in, if we just say L, if we just say L.
But they don't have to be. We could write a reaction in which they flip. We can write reactions in which the R's flip
But then
during the simulation.
But then L wouldn't react with it, right? Anyways.
Only if we tell it
Or
that that's.
Actually, maybe it's important.
So-
Maybe it's important. It's a unidirectional transporter, but the molecule flips.
yeah. Then it still wouldn't work.
Well, say the molecule.
It would work if the L's were on the other side of the membrane. If there were L's on the other side of the membrane after it flipped, then it would transport back the other way.
And that's expected, right?
Yeah, that would be expected.
But then,
But
Whatever. It also.
well, it's not whatever because I mean.
so to take on L then refers to the original orientation of R. But if you flipped R with this notation, then the L's wouldn't react anymore, whichever side they were.
Exactly.
I see.
That's what would
Right, so-
happen.
okay, that's a constraint. Okay.
That's a constraint.
Right. So if R flipped and or L inside of the vesicle, they wouldn't go out anymore. If it's L prime here.
Yeah, if it stayed L prime.
Right. But if we listed it as L, then they would go out,
Right,
or they would go in depending on the direction.
right.
Okay. So it depends on what we want. Okay.
Yeah,
Okay.
this lets you design exactly
Okay,
what you want.
That makes sense.
So if you wanted the other orientation, would you put two ticks?
No, two.
It would just be-
If you wanted the other orientation, you use a comma.
Oh,
So
right,
top and
yeah.
bottom.
Okay.
Right, and we're going to do that. You're going to see that because we're going to make a transporter where this happens, right? So first of all, okay, so this is our first reaction, and it's going to be a reversible. This reaction is reversible. So make sure you click on the double-headed arrow. And the product is going to be LR apostrophe.
We didn't define LR.
Ah,
So this is
right.
fine.
So don't, yeah, so let's leave that off. Yeah, let's add, before we do that, let's go back to our molecules. And we have to add, we have to add another surface molecule that's going to be called LR.
And it's going to have basically the same diffusion as well because L
Right.
assumed to be small.
Right. So give it diffusion constant 1e minus 8. Very good. And then under our reactions, now we're ready to add LR apostrophe. So this is basically the binding and unbinding of the ligand from the receptor where it stays on the same side of the membrane after it unbinds.
Yeah.
So in the forward direction, it's binding. In the backward direction, it's unbinding. And the orientation marks are all consistently oriented, which means there's no flipping or changing or anything like that going on here.
Do you need to set any placement or no? If we're starting
No.
with zero.
So we don't need to place LR because they're just going to form as the reaction happens. But if you wanted to start your simulation with some of them already bound, then you would do that. Right. Okay. All right.
And then we need a rate.
And the rate, yeah. So the forward rate is 4E8. And the backward rate is 10. Really slow. So these are a high affinity. And the forward rate has units of per molar per second, which are standard bimolecular rate constants.
And the upper one would be.
And the backward rate is per number per second, a standard unimolecular or unbinding or conformational change rate constant. Okay. And now if I say run the, and let's go into our plot output settings and let's count LRs. So I'm going to add a count to count LRs in the world. Now I'm ready to run. I'm going to run it. And now if I reload my viz, now you can see I've got at a late moment in time, or if I play time, I get more and more and more of LR forming until it kind of reaches an equilibrium, right? Probably. So if I look at my plots now, I'll see that, well, I'm not at equilibrium yet, but you can start to see some slight curvature to the number of LR in the world. But it's probably going to take a while longer before we reach equilibrium. But let's not worry about that now. Okay.
So you made your simulation run a bit longer than
1,000. 1,000 time steps at 1e minus 6. Everyone getting that to work?
Mm-hmm.
Okay.
What were your rate constants?
4e8 and 10.
And no, just add. Oh, just, yeah.
10. Really slow. Okay.
And we definitely see that they accumulate into the bound state.
Okay. So now let's add, let's turn our receptor into a transporter. So to do that, we're going to add another reaction. Hit the plus button.
No,
And here we're going to say LR tick, or apostrophe, LR apostrophe goes irreversibly to R apostrophe plus
L,
L, comma. Okay.
That makes sense.
Now it starts to make more sense.
You can also just use L without a comma or apostrophe if you want it to be vague, right, or ambiguous.
No, because then
Oh,
it can
well,
be
if you want, so here's a rule. So any reactions involving surface molecules, all the species named have to have orientation marks on them to
So I was
be,
just thinking
so that it's unambiguous. So if
we had
you,
another receptor on the outside vesicle, for example, we'd have to make another reaction with the L comma for that one. Like if we put
yeah.
R on the outside vesicle as well.
well, R is, you mean R on the cell?
On the cell.
On the
Put
cell,
R on the
yeah.
cell. We'd have to
Then
make
you
a
would have
reaction
to,
with R.
you would have to,
L
right, you would have to do that, yeah, yeah. Now, if you didn't care about where the L ended up, or if you didn't care about what the orientation of R was, you would use a semicolon, which is kind of like, you know, kind of like both, right? Yeah. So it's a funny notation, but visually it kind of is easy to read. We spent probably 2 months trying to figure out how to express all this and not miss any of the possibilities. And we had some really ugly ideas in the process.
Would a colon not be better than a semicolon because you have the same symbol on both sides? Did it? If you're saying you're completely not caring, as opposed to a semicolon to suggest that you've got a bigger mark on the bottom that it's bad.
Oh, right, yeah, maybe a colon. But I think we were using a colon elsewhere in the syntax, not in the reactions, and we didn't, yeah.
Yeah.
Yeah, I don't know. You're right, there's lots of possibilities here.
So rate reaction.
And the rate for this reaction is 1,000 per second. Okay.
And then we should add a plot where we measure the.
Inside.
Oh, we already did that.
We already did that, right? So now we're ready to run.
No, I know.
So let's run it.
So now we need Megan's inside the object.
Right.
So now we're ready to run it, and if I load my visualization, now I can see particles ending up inside. They're kind of hard to see because they're still L's. I mean, yeah, there's still L's on the inside.
Oh, yeah. We can also plot L's that are in the cell but not the.
Yeah, and I think I already did that, but maybe you didn't do that. I added L's in or on the organelle. Well, we did that to prove that there weren't any inside when we didn't have the transporter.
No,
So
I'm saying,
now,
can we put them? How many are outside? Like we had. This
oh
syntax
yeah,
before.
yeah, there is a way to do that.
So that syntax doesn't work that we had before. Just to have cell all minus organelle one or.
Right, yeah, you don't do it that way. Well, because this is now an expression that we need to put in how we count them,
Yeah.
not in where we put them, right? I'll show you how to do that in 1 second here. So I'm going to make my plot. And now we can see the L's inside of organelle 1 is now increasing. Whereas previously it would have been 0.
Which one?
The L's inside of organelle 1, now we,
Sorry.
Oh.
For me it says L in or on organelle. Does it say
Yeah,
in?
exactly.
How did you say it's in on?
where,
No, yeah, you're right.
where's that? On
Well,
object?
If it's in
See, it
or
says
on,
count
then it
L
counts the
in.
binding.
In or on. Oh, so here we're just saying that by in or on, we're just being agnostic about whether this is a surface or volume molecule.
Right, but can we?
But-
But oh yeah, because if it's balanced.
L is a
against
volume
R,
molecule, so if I say L organelle 1, it has to be in,
Yeah. Mm-hmm.
because it's trapped, right?
Yeah.
So it's just, we're just being a little bit terse.
Subtract the number of LR.
No.
No, he's
The
saying it's
LR,
just in.
LR is a separate species. So any L has to be either inside or outside. But
Oh, I see, because it's
I
only
see.
L. Yeah, all right, it's kind of cheating a little bit. But yeah, okay, I see.
Yeah, we're just saying,
Okay, that makes sense.
yeah.
Got it.
Okay. So
That's
if we wanted to be able to count how many L's were in the cytoplasm, and not inside of organelle, well, not in the world, we can create a mathematical expression of the counts. And so what we would need to do is count how many are inside of the cell and subtract out how many are inside of organelle 1. Because when we count how many are inside the cell, that's how many are inside the whole cell. And then we can subtract off how many are inside of just organelle 1. And then we would get the total that were outside of organelle 1 but inside the cell.
Yeah,
Okay?
you still wouldn't be able to get in organelle 1 only, because that's looking at in or on.
No, it's the
No, L is a volume molecule,
Yeah, okay.
so it has to be only
Okay,
in.
right.
It's only
You
in.
can't be both or, right, yeah, okay, fine.
Right.
If it was a surface molecule,
It can't be
then it
both
would
a surface molecule and a internal
No,
molecule.
right, because we have a given named species can only be a volume or a surface. It
Okay,
can't
so
be
you have to convert it
both.
from a volume to a surface.
Well,
molecule.
but that's what
That's what
LR.
we're doing. Yeah, I got it.
Yeah, that's what LR. Yeah.
I'm saying we have to do that, yeah.
Yeah.
Makes sense.
Yeah.
Okay. Okay, cool.
Then you can always just.
So you're going to learn tomorrow. You're going to learn tomorrow from Jim that in the BioNetGen language, that molecules combine to form complexes that are composed of each of the individual molecular parts. And those parts can be, some of them can be in the membrane and some of them can be hanging off the membrane, but still be part of the complex.
Yeah.
And this is something that we're working on getting into work in MCell also. Okay, but we're not quite there yet, almost. Okay. Okay, so let's continue. So now we've got our L molecules that have been transported inside the organelle. And let's say that there was an enzyme that was operating on those L molecules, turning them into a different kind of molecule. And then I'm going to call them T's because they're gonna process the molecule and then transport it back out, all in one motion. Okay. So we're going to make a new molecule. And this one's going to be called T1, capital T1. And it's a surface molecule. And it's anchored to a scaffold, let's say, so it doesn't diffuse. So I'm going to give it a diffusion constant of 0. And when it binds our L molecules, it's going to form a complex called LT1. So we better make our molecule called LT1, which is also a surface molecule, also non-diffusible. And after it transports the L to the exterior of the cell, it's going to turn the L into a new form called L2. So we're going to make, while we're at it here, we're going to make a molecule called L2. And it's a volume molecule, and it's going to have a diffusion constant of 2e minus 6. Make sure it's 2e minus 6 and not 2e plus 6. It's very different. Okay. So now we're ready to write the reactions for all of that. So in the reactions, let's add a new reaction. And this reaction is going to say T1 apostrophe plus L comma, because the L is going to be binding from the inside.
But then should T1 not also have a common end because it's an inside phase?
Well, no, it's binding to the backside of. It's binding to the backside of the T1. The L is binding to the back side of the T1.
Yeah. So
Right.
Does that not mean that T1 should have a comma as well?
No.
Why?
So the T1 is in the membrane with its top facing outward.
Yeah.
So there's a diagram that we that we make to help understand the syntax. So what you do is you create a diagram that shows what happens at each step. So here's my T1, and we put it in the membrane. Well, we haven't put it in the membrane yet, but when we do, we're gonna put it in with top front, right? And that means this,
Oh, okay.
right?
Oh, yeah.
But the L
Orientation.
is going to be coming from this side, which is opposite of that. So we say L comma, right?
Is the orientation to the interact, so it's not the time.
Right. Yeah, T1's going to be a surface molecule. Yeah, we will. We haven't done it yet.
I guess it's not. So it's because it's the top of the T1 that interacts, but L1's.
No, it's not the top of T1 that interacts. It's the orientation of T1 at the time of the interaction. And L,
Interaction is T1 prime, which is the top, right?
no.
Prime is a species Q1 that is oriented to the right of inclined prime, which means that the top is prime.
Right.
Yeah, so the front is interacting with something that's, oh, sorry.
No. It's just where the molecules are
Right, okay.
when they interact. So this is opposite of
Oh,
this.
right. Okay, T1
Right.
prime is just indicating the orientation.
Yeah,
Right.
And then this is an irreversible reaction, and
So
then
then-
T1
Okay.
stays prime,
And
and
then
L goes the other.
So then L
turns
comma
into
means
L1
that
plus
L
2.
only
and
L
goes
in
prime as
the
well.
only L inside the organelle, for example, or something like that.
Yeah. Right. Because that's the only way there could be, if T1 is in a fully closed object, the only way there could be L on the back side of T1 is if it's on the inside of the organelle.
Yeah, so L comma means L's interacting with the backside
Right.
of something.
Of something. Right.
Do you mean that to be irreversible?
And-
Excuse me, reversible?
Yeah. So first there's a reversible step where it just forms LT1.
Oh, yeah. Prime.
Right? And the T1 didn't change orientation during that interaction, so the intermediate with L and T1 bound together, that we call LT1, should also not have a different orientation. And two rate constants for E8 and 10. We're not going to be real creative here with the values that we invent. And then we're going to add the transport part of the reaction. Hit plus. And this is where we're going to say LT1. No, I'm sorry. T1.
But I have an error that
Oh.
says reaction directionality required.
Did you?
Oh, you must have
Or a tick?
you must have left off a comma or a tick.
LT1 is used in every
Where was it on top?
T1 still prime and L. No, now we need a chemical reaction.
Did you define the molecule?
Oh,
You define LT outside that. Or LT out.
T1 goes to T1 prime and L2 del comma.
Okay. So now we're gonna now we're adding another reaction, which is going to be LT1 apostrophe irreversible goes to T1 apostrophe plus L2 apostrophe.
Oh, it's getting transported and reacted at the same time.
Yeah. You could break this down into separate steps, but we're kind of mushing it all into one step.
Yeah. We could even have a reaction intermediate.
Yeah, anything you want. Okay, and this rate constant is 1,000 per second. And now we just need to release T1s somewhere.
What was this is the new format.
So we're going to put T1s. We're going to make another release site. Keeps doing this thing where it seems to be off by 1 and it's counting somehow. I'm going to release, on release site 3, we're going to release T1s. And we're going to put those onto Organelle 1 again. And we're going to put 1,000 of those. So we're going to have a whole bunch of those. Okay.
And then we want to plot something else.
Yep. So in our plot output settings, we're going to count T1s in the world or wherever you want. I'm going to count LT1 in the world, and I'm going to count L2s. Okay. And now we should be ready to run it. I'm going to clear my runs and run it.
That's a lovely.
That's a lot of T1 on there.
Yeah, a lot of T1. And most of them uncomplex. That's the time point that
I expect more things within the organelle.
yeah, because now they're getting pushed out, there should be less things in the window.
Uh-oh.
What,
What's going on here with my L2s?
I have those too. There aren't very many of them, but there are some. Yeah.
Yeah. I'm getting L2s, it's just taking a while to see them happen. They happen late in the process. Okay. So one thing I just did that some of you may have noticed is that if I'm in the molecules panel, there are some icons next to each listed molecule, and one of those icons is the magnifying glass, and the magnifying glass means show just that one, hiding everything else, right? Or I can click on the little eyeballs next to them and show more and more. Another thing you can do is on the right side of the molecules panel, below the plus and minus is an eyeball and a closed eye, which shows or hides all of the molecules.
And then you can take an eye on an individual molecule and turn that one over, not so far.
Right. Exactly.
I'm not sure.
Okay? But I'm going to show them all. Okay. So now next, it looks like it's going to take. I'm going to look at the plot.
Yeah, and I think you need the same on the plot as well.
If I look at the plot, oh, now something really interesting happening in the plot. We're starting to get L2s starting to form, but there aren't very many. But look at the L's inside of Organelle 1. Previously, those were going up and up and up, but now they're kind of going, they're kind of stochastically fluctuating there because their numbers are being held very low, because the L's, not very soon after they are transported in, start binding to the T1. And so LT1 in the world is going up as it binds the L's that are transported into the organelle. Okay, but it's taking a long time for this to happen, so let's run for a little longer. So I'm going to go into the run simulation panel. I'm going to change the time to 20,000 iterations, or 20 milliseconds of simulated time. And I'm going to hit save. Haven't hit save in a while. And now I'm going to hit run. And it's taking a little bit longer to run. That's kind of pretty slow. So I'm going to kill it. And the reason why it's running slow is because we haven't done the partitioning. So I'm going to go in and I'm going to say include partitions. I'm going to say automatically generate. And this time the settings are just fine the way they are.
Mine are a little different, like 0.518 or 0.482, that's okay. Maybe because my circle is a little in the center.
Yeah, could be. So yeah, don't worry about that. It automatically adjusts itself to fit the bounding box of your objects.
How many iterations did you set up?
20,000. So now I'm going to run it again after setting the partitioning. And now it's running a lot faster. Still not as fast as before, but
it's more steps.
we're running for more steps and there's a lot more going on.
We're still getting 500 iterations per second.
Yeah, it's not bad. And don't forget that as we're computing all this, we're writing out the output of all the locations of every particle so that we can look at them. And there's an option for turning that off. If you're running on a big supercomputer and you're doing production runs, you can tell it to not output any visualization data and just output the numeric quantities, right?
It outputs the location every time step of every molecule.
Right. That's what this is. That's what's happening now. So, okay, mine's finished.
Yeah.
I'm going to say reload, and now I can, if you click, you can hit the run button and watch it run, right? But I use for something like this, I like to pause it, and then I can click and drag on the time cursor, which is this bright green line.
Awesome.
And scrub back and forth and watch the whole thing go. And then I can do the plot output and look at it. And now we see some interesting dynamics, right?
Yeah. LT1 particularly.
Yeah. So L2 is coming up to a pretty high number. The maximum number we're going to be able to make is about 1,000, right? Because we're conserving mass and we're converting 1,000 A's into L's into L2s, right? Eventually we'll convert them all. After 20 milliseconds, we've gotten about 3/4 of them.
The RS are probably bound to give our...
Yeah, that's true. That's true. Okay.
Yeah, we still have 25 LRs and 20 LT1s in mind.
Yeah. And you can see the stochastic fluctuations in the shapes of these curves, which is telling you something about the noise characteristics and the variance. Okay, but we're not done. Okay. So, but we're not quite yet done.
I don't know which one. Wouldn't this be
We're going to add another model object. So in my picture I drew over here, I drew 2 organelles. So go to the Model Objects panel and make sure your cursor is centered. And then add another Ecosphere. And it comes up with this giant thing because it would have remembered the settings from before, except that we quit Blender and restarted Blender. So I have to go back and make sure I go to 4 subdivisions for the Ecosphere. And I'm going to set the radius to be 0.175.
We're making another.
Yeah. So I've made an Ecosphere with 4 subdivisions, and its radius is 0.175 microns. And so after you've created it, you'll see a picture like this. And then I'm going to drag the new object off to the side, being careful not to move it all the way so it out of the cell. And then we're going to change its name to Organelle 2. And add it as a model object. Yeah.
Subdivisions and size is going
4 subdivisions and a radius 0.175.
Yeah, you can close.
0.175. And then I'm going to make it transparent also. So I'm going to add, under its options, I'm going to say add material, make it transparent in both senses, and 0.3 say for the transparency, and hit save to save it. Okay. And now we're ready to make a new molecule.
Do we not want to change the releases of the other ones to not go into that?
Well, that's a good point. James brings up a good point. So in our molecule placement for release site 1, where we release Ls, we now need to tell Ls to not be released inside of organelle number 2. And you can do this by saying minus organelle 1 all minus organelle 2 all, but I'm going to say minus, I'm going to say cell all minus parentheses.
Where is this?
This is in the molecule placement for release site 1. Yeah. So notice what I'm typing here. This is in the release site 1 for the object region to release. I'm going to say cell all minus parentheses organelle 1 all plus organelle 2 square bracket all square bracket and then end parentheses. Okay, so the plus sign is the Boolean union operator. So that means it's the union of the volume of organelle 1 and organelle 2. And then we're going to subtract that union from cell all. Okay?
Is there an advantage to doing it this way instead of minus organelle 1 minus organelle 2?
I guess it's easier to keep track, maybe.
Yeah. It's for that reason, right? It would work either way, but I think conceptually it's easier to keep track of it this way. Okay.
Yeah. What's the new organelle's name?
Organelle 2.
Is there any other properties that you went over right after? So I made it transparent. I determined the size. I got the molecule placement to exclude anything from that space,
Yeah,
and I put it inside the cell. Is there anything else that I missed?
No, I think that's it. So your picture should look
Yeah.
like this, and for your molecule placement for release site 1 should look like this. I think that's all I did.
Yeah.
Yeah.
And now we were going to make another molecule.
Yeah, now we're making more molecules. Okay, so now we're going to make another transporter
T2.
called T2. Good guess. And it's going to be a surface molecule, that's not diffusible. And this is the transporter that is going to sequester our product, L2. So it's going to react with L2. So we're going to get an intermediate called L2T2. So let's make that molecule. And that's going to be a surface molecule. That's non-diffusible. And then after it sequesters L2, it's going to convert L2 into L3. So let's make L3, which is going to be a volume molecule. And its diffusion constant is going to be, okay, 2e minus 6. Okay.
Just going really fast.
Okay. Okay. Okay.
So what is T2 again?
Oh, I'm sorry. So T2 is going to be a transporter, a volume molecule. I'm sorry. Yeah, I am going pretty fast. And it's a surface molecule. T2 is a surface molecule with no diffusion constant. And then L2T2 is going to be the complex, the bound complex. No, with no diffusion constant. And then the product that's going to be made is going to be called L3. And it has a diffusion constant of 2e minus 6. And it's a volume molecule. Okay.
Then we copy the reaction again.
Okay, so now we're going to make reactions.
Oh. Did you add something to molecule placement?
Yes. Yeah. So to molecule placement for release site 1, since we added an organelle 2, we also need to exclude it. And the way I did it was I put parentheses after the minus sign. And it's organelle 1 plus organelle 2 inside of parentheses. Yeah, a curved parentheses.
Then can we make this one the transporter flip?
Yep. It's going to transport to the interior of organelle 2, but it's going to transport L2 and turn it into L3.
Yeah, which
Yeah.
can flip as well, so that after a while it stops doing that.
Right.
I don't know, make L3 get stuck in
That's
the
right.
And then you get
So everything will be stuck as L3 in the end.
Yeah.
Well, it depends on whether you combine the reaction or not. It could be you stop making L3 and end up with more L2.
All of it should be converted to L3 in the end, because there's no
Yeah.
space in it.
Because the L2s are going to be pushed out.
All of Flux is
Oh yeah, you
The-
still do the conversion.
We're going to put the T2s onto organelle 2.
Yeah.
We haven't done that yet, but we're going to. First, let's make our reactions.
Well, we can do that as well.
Okay, so in the reactions, we're going to have a reaction between T2 apostrophe plus L2 apostrophe, reversible, which makes a product called L2 T2 apostrophe. And the rate constants are, as before, 4E8 and 10. Okay? Oh, yeah, I'm sorry. I'll put my mouse so you can see. Okay, 48 and 10. And now the final reaction that we need is L2T2 apostrophe. Irreversibly makes T2 apostrophe plus L3 comma. And the rate constant of that is 1,000 per second. And save. And now we need to place our molecules. So we need a new release site that is going to be called release site 4. I keep getting, that error just keeps generating.
My one, it generated the first time and then it was fine after that.
Yeah, and mine just keeps doing it. And Bob and I tried to replicate it yesterday on the airplane flying out. We saw it happen once and we could never replicate it again. And so we could never, we looked at the code and we couldn't figure out, yeah.
The same computer, sometimes the same thing.
Yeah.
Except this time it's literally above.
Yeah. Yeah, why do computers sometimes cluster together in the dark, in the corner at night?
Why?
No, that was a line from iRobot. That was in Isaac Asimov's thing about, these artificial intelligent machines someday, what they might do. Anyway, geeky moment. We're gonna put T2s onto Organelle 2 with an orientation of top front. Organelle 2.
And you place the amount, so 1,000?
Yeah, and we're gonna put 1,000 of those.
And then we need more costing as well.
Okay. And yeah, and plot output settings so that we can count those states. So we're gonna count T2s in the world, and LT2s, and L3s. Okay, and now we're ready to run. Export and run. Crash. Okay, so it happens to me also. Hopefully I had done a save. I don't think I did.
Is this just
I'm
happening
gonna
in this
trace
version,
back
or does
from
this
the-
usually happen in there?
Invalid stop sign.
Before like this, so I don't know what's, I don't know if it's the environment,
Yeah. I don't know.
Oh, mine's crashed out here.
It's been incredibly stable
Okay.
for
What do you see
for years, like incredibly stable. And then I'm not sure what's going on. I'm just
You made a package.
yeah, we made a package. Made it.
Oh,
So the red.
I opened it again and now it's
accumulating.
as if it's run the simulation, the molecules are there.
Yeah.
Yeah. I got the
Well-
same thing.
Went back to red.
Except I have.
Yeah. I think it ran some of the iterations, but maybe not all of them.
All three same
Oh,
colors help.
It ran out to
Yeah, it's
20,000.
fine.
mine ran all the way.
Mine did too.
Yeah. So I think it was Blender that crashed and not M-Cell.
And why would Blender crash?
I don't know. It's incredibly stable. And
Except when you,
except when it isn't, and yeah.
All the colors are used.
So I'm going to run mine again.
maybe you ran out of color.
Yeah.
No, there are colours. Although
Yeah,
we now have two objects that are red.
So I'm running mine again,
Well, we can make
just
it
to see it complete all the way.
No, I can't see any molecules on mine.
oh, we need to actually plot, or get the plot.
Maybe you hit all your molecules and left it in that state.
No, apparently it hasn't actually run anything.
Oh, okay.
Oh, here we go. Now it's going.
So, okay, I see. So when you compile it, it does it piecewise. So like at 10%, you can go through 10% of the time steps.
Yeah.
So then once you press play, all of it's already compiled and it's just reading it off the log file.
Yeah.
Okay, cool.
It ran all the way.
Okay, so mine ran all the way. Again, it didn't crash after doing that. So, okay.
How, so, okay.
So now you can see that inside of Organelle 2, we're sequestering a lot of the L3s inside there. And if I look at my plot, which is kind of hard to see with all the legends popping up. So there's a way to turn off the legends. Maybe just briefly, in my case, I'll say no legend.
Yeah. And then molecules.
And then,
so we know what they are.
yeah, because each plot is a separate plot that's labeled on top, so we know what they are.
Okay, now my turn.
And so now the number of L2s in the world reaches a peak value of only about 114 or so, and the L3s are increasing.
I don't have a plot for my teacher.
Yeah, I guess show it all through first.
Oh.